My name is Arjun and today we are going to discuss Kahn's algorithm for topological sort. So let us first try to understand what topological sorting for a directed acyclic graph is. It is a type of linear ordering of vertices such that for every directed edge uv, vertex u comes before v in the ordering, and the starting vertex should always have 0 in degrees. In degree is nothing but the number of incoming edges towards a vertex. So let us try to understand this from this graph. We can see that the vertex 5 and 4 have 0 in degrees, as 5 and 4 have 0 incoming edges. 2 has 1 incoming edge, so its in degree would be 1. 3 has 1 incoming edge, so its in degree would be 1. 1 has 1 incoming edge, so its in degree would be 1. And 0 has 2 incoming edges, so its in degree would be 2. So we can either start from vertex 5 or vertex 4 because they are not connected and it doesn't matter which order we go for. So let us suppose we start from 5. So our topological sorting order becomes 5, 4, 2, 3, 1 and then 0. Or if you start from 4, the order becomes 4, 5, 2, 3, 1 and 0. So in the graph 2 comes before 3, 3 comes before 1 and 5 comes before 2. So in our final sorted order, this should also be the case. So 5 comes before 2, 2 comes before 3 and 3 comes before 1. And in this order as well, 5 comes before 2, 2 comes before 3 and 3 comes before 1. Next we have two more examples. Let us see. In the first example we have B, E, C, A, D. In this graph we start from B as it has 0 in degree. If we start from B, we have two adjacent vertices E and C. If we remove B, the in degree of E becomes 0 and of C becomes 2 from E and A, so we move towards E. If we remove E, the in degree of C becomes 1 from A and that of A becomes 0. If we move towards A and we remove A, the in degree of C becomes 0, so we move towards C, and we remove C, in degree of D is 0, we move towards D and we remove it. So the order becomes B, E, A, C, D. Similarly, in the second graph, we can either start from 0 or 3 because both have 0 in degrees. So we go from 0, 3, 4, 1 and then 2. Next, why topological sort doesn't work for cyclic graphs? This is because the order might change. So we have a cycle over here from 0, 1, 2. Let us suppose our sorted order is 0, 1, 2. But from the graph, we can see that 2 comes before 0 and after 1. But in this order, it is not true. 2 comes after 0 and not before it. Similarly, for 0, 0 comes after 2 and before 1. So before 1 condition is satisfied, but after 2, it is not true. So topological sort doesn't work for cyclic graphs. So Kahn's algorithm. The step 1 in Kahn's algorithm is to compute the number of incoming edges, which is the in degree for each of the vertex present in the graph, and store it in an array. Then we traverse through the entire array, and as we encounter an in degree 0, we add it to the queue, and then we perform BFS. So we remove that vertex from the queue and add it to the result array, and we decrease the in degree by 1 for all its adjacent vertices. If the in degree of adjacent vertices is 0, we add it to the queue, and we continue to repeat this process until the queue becomes empty. The final topological order is stored in our result array. So let us understand it from this graph. Suppose we have this graph 1, 2, 3, 5, 4. The in degree of 1 is 0 as there are no incoming edges. In degree of 2 and 3 is 1 because of one incoming edge from 1. In degree of 5 is 2 because of incoming edges from 2 and 3, and that of 4 is 1 because of incoming edge from 5. So here 1, 2, 3, 4, 5 represent these vertices, and 0, 1, 1, 1, 2 represent the in degree of each of these vertices. So we traverse through this array and we find out that the in degree of 1 is 0, so we add it to our queue. Next we remove it from the queue, and then we update the value of 2 and 3, which are the adjacent nodes of 1, and we decrease them by 1. So after doing that, the in degree of 2 and 3 also becomes 0, so we add it to the queue. Next we remove 2, so the in degree of 5 becomes 1 from 3. We remove 3, the in degree of 5 becomes 0, we add it to our queue. So after adding 5 to the queue, we remove 5 from the queue, and then the in degree of 4 becomes 0, so we finally put 4 into our queue and then we remove it. So our final order becomes 1, 2, 3, 5, 4. So We also have another order 1, 3, 2, 5, 4 because 2 and 3 are not connected and they can be removed in any order as we want. Pseudocode. Suppose we are given a vector matrix edges, number of vertices and number of edges. We create an adjacent list which contains the adjacent nodes of a particular vertex. We create an answer vector in which we will store a topological order. So first we push back all the adjacent nodes of a given node. After that, we have to calculate the integrity. After calculating the integrity, we traverse through the integrity array, and if we find that the integrity of any of the vertex is 0, we add it to the queue and we remove it from the queue, put it in the answer array, and continue doing this process until the queue becomes empty. So finally, in the end, the topological order is stored in our answer array, and yeah,